Okay, this lecture is on chapter 9 from your textbook. So first we'll talk about using uncertain knowledge. In AI, agents rarely have complete knowledge of the world, so they must act under uncertainty. In cybersecurity, this shows up as incomplete visibility into system activity. We don't directly observe compromise. Instead, we observe partial signals and must make decisions based on them and make inferences from them. So again, AI assumes limited observability, and cybersecurity is a clear example of that. Logs may be missing, they may be delayed or noisy, and attackers actively try to evade detection. So there are things that aren't visible that you can't see. This means the state of the system is only partially observable, which makes uncertainty a fundamental part of security analysis. So why probability? Probability provides a formal way for AI systems to reason under uncertainty. Instead of making binary decisions, the system assigns likelihoods to different outcomes. In cybersecurity, this allows us to estimate how likely activity is to be malicious and prioritize responses accordingly. From an AI perspective, alerts are observations, not ground truth. The same observation can be generated by different underlying causes. For example, a PowerShell alert could reflect normal administrative behavior or malicious execution. The task is to interpret signals, not assume that they are definitive. Conditioning is the process of updating beliefs when new evidence is observed. In AI, this means adjusting probabilities based on incoming data. In cybersecurity, this happens during investigation, where each new alert or log changes the estimated likelihood of compromise. And this slide is an example of sequential evidence updating. Each event contributes to the overall belief state. In cybersecurity, risk is not determined by a single signal, but by how multiple signals combine over time. And AI systems model this by continuously updating probabilities as new observations arrive. And in probability, Bayes' theorem provides the mathematical framework for updating beliefs. It allows an AI system to compute the probability of a hypothesis given observed evidence. In cybersecurity, this translates to estimating the likelihood of compromise given certain alerts and other signals. And a key issue in AI is distinguishing between likelihoods in different directions. Security tools often tell you the probability of an alert given an attack, but analysts need to know the probability of an attack given an alert. And Bayes' theorem allows us to invert this relationship and incorporate base rates, which is essential for reducing false positives. So that's how Bayes' theorem is used. So why is Bayes' theorem interesting? Bayesian reasoning supports diagnostic inference, where we move from observed effects to hidden causes. In AI, this is common in domains like medical diagnosis and fault detection. In cybersecurity, we use it to infer attacks from observable signals like logs and alerts, and from those signals to infer that an attack may have happened. And cybersecurity can be modeled as a diagnostic AI problem. The true system state, such as whether a system is compromised, is hidden. The AI system must infer that state from observable evidence. This aligns directly with probabilistic reasoning and sets up the use of graphical models and temporal models. And now we'll talk about belief networks. In AI, a belief network is a way to represent how variables depend on each other using a graph. Each node is a random variable, and edges represent direct dependencies. Instead of treating everything as independent, the model captures structure. In cybersecurity, this is useful for representing how different events and conditions relate to one another. A belief network maps naturally to how attacks unfold. One event increases the likelihood of another. For example, credential theft can enable lateral movement, which can lead to privilege escalation, which can lead to data access. From an AI perspective, we are modeling conditional dependencies between variables rather than treating each event in isolation. And the fire alarm model that you see here is a classic example of probabilistic reasoning. The system does not directly observe fire, but it observes signals like smoke and alarms. In AI terms, fire is a hidden variable, and the others are observable variables. This structure allows the system to infer the probability of fire given what it observes, such as observing smoke, fire alarm going off, people leaving the building, and so on. Now, in cybersecurity, we replace the fire example with system compromise. Alerts and anomalies act like smoke and alarms, and it, otherwise functions similarly. The AI system uses observed signals to infer the hidden state of the system. This is the same structure as the fire alarm model, just applied to security data. And in summary, on belief networks, a belief network is a directed acyclic graph where each variable depends only on its parents. This reduces complexity by encoding independence assumptions. In AI, this makes probabilistic reasoning tractable. In cybersecurity, it helps avoid overcounting evidence and supports more accurate inference from multiple signals. And now let's talk about why structure matters in SIEM. Without structure, an AI system might treat every alert as independent evidence. That leads to inflated risk estimates. By modeling dependencies, the system can recognize when multiple alerts come from the same underlying cause. This improves correlation and reduces false positives in SIEM systems. And now we'll continue talking about understanding independence in terms of common ancestors. In AI, when two variables share a common cause, they are dependent unless we know that cause. In cybersecurity, multiple alerts may be generated by the same compromise. Without knowing the root cause, those alerts appear related. Once the cause is identified, their relationship becomes clearer. And this is the practical version of common ancestors. A single compromise, such as a stolen account, can produce multiple alerts across systems. From an AI perspective, those observations are correlated because they share a hidden variable. Recognizing this prevents double counting of evidence. In other words, that multiple alerts does not necessarily mean multiple attacks if they're all stemming from the same attack. And then we'll talk about understanding independence with the chain structure. A chain represents a sequence of dependencies. One variable influences another, which influences the next. In AI, this models causal or temporal relationships. In cybersecurity, this aligns with attack progression, where earlier steps lead to later ones. So, speaking of attack progression, in practice, attacks follow a sequence such as initial access, persistence, and escalation. Observing later steps increases the likelihood that earlier steps occurred. This is an example of inference along a chain where evidence propagates backward and forward throughout the model. And now we'll continue talking about understanding independence in terms of common descendants. In AI, when two variables influence the same outcome, they are initially independent, but can become dependent once we observe that outcome. This is known as a collider structure. In cybersecurity, different causes can produce the same alert, and observing that alert links those causes together. So applying that to cybersecurity, this slide is the practical effect of a collider. A single alert, such as outbound traffic, may have multiple explanations like malware or legitimate software. So one would be a malicious reason, the other would be benign. When evidence supports one explanation, the probability of the others decreases. This is called explaining away and is a key idea in probabilistic reasoning. So explaining away the other competing explanations. And in belief networks, all relationships can be reduced to three patterns, like we just talked about: chains, forks, and colliders. These define how information flows through the model. In cybersecurity, these patterns appear in attack sequences, shared root causes, and competing explanations for alerts. That would be the corollaries to each of these three. So once again, to directly apply that to cybersecurity, like we were just talking about, the three patterns in security data. These three structures map directly to real security problems. Chains represent attack progression. Forks represent shared causes like compromised accounts. And colliders represent competing explanations. Recognizing these patterns helps AI systems and analysts interpret alert relationships correctly. And finally, the last few slides I have talk about Markov chains and hidden Markov models. So starting with Markov chains, a Markov chain is a model where the next state depends only on the current state, not the full history. In AI, this simplifies reasoning over time. In cybersecurity, this allows us to model how a system moves from normal behavior to suspicious activity and potentially to compromise. So in practice, in cybersecurity, systems state evolves step by step. A system might move from normal to suspicious, and then suspicious to compromised. Each new observation updates the current state estimate. It might even go through a high risk state, for example, before it even becomes suspicious. But in either case, no matter how you define the states, the next state depends on the current state. And this is used in user behavior tracking and anomaly detection. So each new observation updates the current state estimate, and AI systems use this idea to track behavior over time rather than evaluating events in isolation. And a hidden Markov model extends this idea by separating hidden states from observations. The true state, such as whether a system is compromised, is not directly observable. Instead, we observe signals like logs and alerts. The model connects these observations to the hidden state probabilistically. And so to apply that concept to cybersecurity, we can talk about inferring compromise from observed signals. And this is the core AI problem in cybersecurity. We observe signals, but we care about the hidden state of the system. By combining multiple observations over time, the system estimates whether compromise is likely. This is how modern detection systems move from raw data to actionable decisions. And that concludes the slides for chapter 9.